Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 19. The title of this lecture, Design with PLA, of the course Digital Logic Design of Chapter 4, Design with Standard Modules. This disclaimer is for you to read. There are many references in digital logic design. In my lectures, I follow reference number 1. In Chapter 4, the contents are decoders, decoder expansion, design with decoders, code converters, encoders, multiplexers, multiplexer expansion, design with multiplexers, demultiplexers, read-only memory, and design with RAMs. And today we will talk about programmable logic array and design with PLA. What's a programmable logic array? A programmable logic array, or for short PLA, contains an AND gate array and an OR gate array. Both arrays are fully programmable. Like the RAM, a PLA with n inputs and m outputs can realize n functions, each of which has n switching variables, or can have n switching variables. Now, since both arrays are programmable, the AND array and the OR array, the functions need to be represented as sum of products. Sum of products, we have to minimize the function using plain algebra or K-map to the minimum possible. Then we implement the product terms in the programmable AND array. Then we implement the sum of the product terms, or we OR the product terms in the programmable OR array to represent the functions, the output functions. To implement switching function with a PLA, we must first simplify the function as sum of a product form. The AND array will realize all required product terms of the input variables, and the OR array will OR together the required product terms to form the output functions. The content of PLA can be specified by a modified truth table called PLA table. We will see it shortly. With the symbols 0, 1, and dash on the input side of the PLA table indicates whether a variable is inverted, not inverted, or not present in the corresponding product term when we use dash. The output side of the table specifies which product terms appear in each output function, where the symbol 0, 1 indicates whether the product term is absent or present respectively. Now, as an example, we will take the x3 to the BCD converter. So ABCD are the inputs, and WXYZ are the outputs, which is the BCD output, and this is the x3. So when we have the input 0, 0, 1, 1, the output will be 0, 0, 0, 0. When the input is 1, 1, 0, 0, the output will be 1, 0, 0, 1. Now we went to K-map and we simplified the switching function W, X, Y, and Z, and we find W is AB or ACD, X is B prime, D prime, or B prime, C prime, or BCD, Y, C prime, D, or CD prime, and Z is D prime. Now the terms has to be represented as a product term. For instance, C prime D or CD prime is C exclusive or D, but we cannot use an exclusive OR here. It has to be product term because we have an AND, programmable AND array to form the product terms. And we have programmable OR array to make the sum of those product terms. So from this data, once we have W, X, Y, Z, we can represent the PLA is shown in A. We can construct the PLA table given in figure A here. So we have the input A, B, C, D, and the output W, X, Y, Z. So we look at each product term. For instance, when we have D prime, the last one, D prime, A, B, and C, they are not connected, so we put dashes. For D, we put 0 because it is complemented. Okay? And here, the output function here, the output W, for instance, it's equal to D prime only. W is equals AB or ACD. Apologize. Z is equals to D prime only. So when Z is equals to D prime only, if we look at the output function here, okay, all those product terms are not selected. The only product term selected for Z is 1, is when we have D prime. And D prime is not used for W, X, Y, so we put zeros. So the only function uses D prime is Z, and we have 1. Let's take another example. Let's take the example we have C prime D or C D prime for Y. So we go here, C prime D and C D prime. C prime D, we have dash dash, C is 0 because it's inverted C prime, and D is 1. C D prime, we have dash dash, C is not inverted, so it is 1, and D inverted, so it is 0. Okay. Now Y uses both. So I have Y, 1 here and 1 here, and 0 in all other product terms. So Y will be 1, 1. And this is indication that Y, so this will be basically the outputs. So this is the programmable AND array, and this is the programmable OR array. So let's see how the hardware all works. I have A, and I have inverted A. And I have B and inverted B, C and inverted C, D and inverted D. So to generate D prime, I need only one dot. A dot represents a connection, or X represents a connection. So D prime is here, so I generated D prime. The output Z is taking D prime, so this is the line is D prime. Only Z uses D prime. So Z is not using anything else. All the product terms, see, there is no dots or no axis. The only dot here indicates a connection with D prime. So when we program the chip, this fuse will be intact and all the other fuses will be blown. So this will be the output Z. The same thing with Y. Y, we did C D prime and C D prime and C prime D. So we picked up those two to represent the output Y. So it is C D prime or C prime D. Those again generated from the corresponding, I have C prime and D, and I have C and D prime, C and D prime to generate the product term, C and D prime. Okay, so the hardware is really a translation to the real table. So we can construct the PLA table given in figure A with one row from each distinct product term. Figure B shows the corresponding PLA structure where a dot at the intersection of a word line and an input or output line indicates the presence of a switching element or a connection, and the AND array or OR array respectively. In the AND array or OR array respectively, the PLA has 4 inputs and 8 product terms and 4 outputs in this case. So to pick out the right PLA, we have to have at least 4 inputs and 4 outputs, and at least we have a total of 8 product terms. So the size of the PLA that you choose must be appropriate for your design, and this is very important because otherwise the switching functions are not going to fit. Often, actually, those PLAs are much larger than the problem on hand, and you can implement them. The problem on hand, you can implement it very easily on a PLA. So this is the concept how PLA is used. So the PLA, again, has a programmable AND array and has a programmable OR array. So unlike the RAM had only the OR array was programmable. The AND array was fixed. We generate all the midterms. And the function was represented as canonical standard form as a sum of midterms. But here we simplify the function and we implement each and every product term using the AND matrix. So everything's programmable, and this is more efficient design because you will simplify the hardware much to a very high extent. However, if you have really a large number of switching variables, the RAM would be the choice to implement any switching function. Now, this would be the last slide for this presentation. I would like to thank you so much. Please subscribe, hopefully to see you soon. Sincerely, Dr. Hassan. To subscribe, there is a blue circle with a letter I inside it. So please click on the blue circle. Thank you so much. See you soon.